All right, we have a lot to cover today. I'm basically going to recap the entire past 4 weeks or so of classes. As some of you may have noticed from the syllabus, next Tuesday is the first midterm. So, in preparation for that, we're going to talk today about, we're going to recap everything that we've gone through, and we are going to go through some examples, and we're going to look at what you need to recap, what you need to know, and this is basically your opportunity, your last major opportunity to ask me questions about pretty much anything, particularly things that are going to be on the exam. So, the first thing I want to cover is the idea of, first thing I want to cover is transitions from the way that we ask questions in a database. So, over the course of the term, we've been talking about a couple of different ways of phrasing queries. So we've been talking about SQL as a starting point. SQL then has all of these corner cases that makes it very easy to express queries, but makes it a lot harder to process them. So we introduced this language called relational algebra that gets rid of these corner cases, that is a lot easier to deal with, at least from the database's perspective, and that allows us to actually process and optimize these queries more effectively. The relational algebra gives us kind of an execution plan, a way of defining a set of iterators that compose together to produce the final query result. So the first thing I want to do today is go through a couple of examples of this whole process, of going from SQL to relational algebra to the actual iterators and that are used to evaluate a relational algebra expression. So we're going to start off with a really straightforward query. Some of you may recognize this from the workloads, the example workloads that you were given. This is one of the players' queries that you were given. So the idea behind this, one of the slides lecture has this basic you'll see this diagram pretty much throughout the entire slide deck. This is essentially your guideline for how to do the translation. Whenever you do a translate SQL to relational algebra, you basically start at the bottom of this diagram and work your way up. So let's see if I can get both of these on the screen at the same time. Okay, so where do we start? If you want to translate this query, what's the kind of bottom of the relational algebra tree that we'd like to create? The from clause. Okay, so we start with the from clause. In this case, what is that? Players. So we take players and we start from there. Okay, what's next? So moving up the tree, we have players. What's next? The where clause. Okay, so we're going to take the where clause, and the where clause corresponds to a selection operator. Selection operator created by sigma. That gives us a condition to evaluate over players. All right, what's next? Projection. Okay, so the last thing, let's go through this. The aggregate operator only applies for aggregate queries. This has neither aggregate functions nor a group by clause, so this is the aggregate query doesn't apply. There's no having clause, that doesn't apply. And the next thing up is the projection, which in this case we want the first name, last name, and first and last seasons. All right. Do we have anything else? We have an order by clause. No. Distinct clause? No. Limit clause? No. Since we don't have any of those clauses, we can pretty much ignore this outright. Again, there's no union clause. So basically we have a tree of relational algebra operators that corresponds exactly to this select query. All right, I have a little bit of sample data here, just so that we can actually try this out. So we have our relational algebra tree here. This. What is that? Is that visible? Kind of. It's some data. I'll call it out when it's necessary, and it will be scanned and put in for you later. So, as we're evaluating this, where do we start? You've been at too many office hours. Someone else, where do we start? Players. Okay, so we can evaluate each of these compositionally. So we're going to start at the bottom. We're going to basically outright ignore everything from everything above players. And we can define an iterator class that can iterate over the elements of players. So we can define a getNext, and when we call getNext the first time, assuming that our data set is what you see up there, what would we get when we call getNext on players the first time? The first row. All right, so that's Desmond Farmer. All right, and then again, second row. Okay, so Martin Phil. And so forth. Now, this iterator is going to have to read in the CSV file. It's going to have to split apart all of the rows of that CSV file. How would you actually represent the output? How would you represent one tuple, the return value of this from this getNext function? as an array of what? Okay, so we could put one column in each array. Farmer D01, Damon, Farmer 2006, 2008, 220, and so forth. What kind of data representation do we use? What kind of object? What class do we use to represent every element of that? Well, okay, so the tuple is an array. The tuple and row mean the same thing. Okay, so you can store it all as strings. Now what happens when you actually need to evaluate? Well, we'll get to that in a moment. So you can store it all as strings. I want you to hold on to that, and we'll get back to it in just a moment. All right, so now we've defined something that can iterate over the rows of a relation. Now, we can also define something that iterates over the output of a filtering predicate. And the cool thing about relational algebra is that every operator operates on a relation. It does not care what comes in beneath it. So if we want to define an iterator for select, how would we go about doing that? So the select, let's move to the chalkboard to give ourselves, so the relation iterator splits and returns one line of my CSV file. How can we define something similar for selection? Or what would selection need to do? Yeah?
Get next, compare and decide whether to return or not.
Okay, so select is defined in terms of some other iterator. Let's call it source. And in order to do get next, you need to call the source.getNext. That gives you a row from your input. And you need to figure out whether the condition is true for that specific row. How do you do that? So how is the expression defined? If I give you this ls minus fs is greater than 5, how is that encoded?
You remember the index numbers and then give the value from the function.
Might be skipping ahead a little bit. So eventually, yes, you do want to extract. The columns corresponding to ls and fs, or the values of those columns for each row. But even before that, I give you a string. This string that's written up there, ls minus fs greater than 5. From the computer's perspective, it's not storing that as a string. It wants,
It's an expression.
it's an expression. So it's an expression. An expression is essentially a tree structure, just like the ones we're using for relational algebra. Except in this case, the tree structure is based on the semantics of just regular arithmetic expressions. So we have one node in this tree that represents a greater than comparison, and that is going to have a left-hand side and a right-hand side. The left-hand side corresponds to that expression, which can be represented as a subtraction between, again, a left-hand side and a right-hand side, ls and an fs, And then the right-hand side of the greater than comparison is the constant 5. So there's an expression in here. And if I plug in a specific value of ls and fs, I'm going to get back some result. For the purposes of your project, there's code that actually evaluates this for you, the eval class. But let's say we plug in some specific values. So the first row here is Desmond Farmer. So if I plug in last season, you get 2008. And if I plug in 2006 for first season, I can now reduce this expression. It has no variables in it. I can reduce it down to 2008 minus 2006 is. I know you're computer scientists. I can't do math either, but. All right, so this whole thing reduces to 2. 2 is not greater than 5, so this whole thing reduces to false. And I can do the same thing, just iteratively plugging in numbers for ls and fs, and I can evaluate this expression for every single row of my input. Now, for the most part, you don't actually need to care about any of that, except for that plugging in part. So for the purposes of your project, the eval class has no idea how you're representing rows, so you're going to need to plug in something in there. All right, but at any rate, let's say that we plug in some numbers for our data here. We call getNext on our input. We get farmer DE 2006, 2008, blah, blah, blah. The expression, if we plug in 2008 and 2002, the expression evaluates to false. So what do we do at that point? Move on to the next row. So this returns false. If it returns true, we return the current row. If it returns false, we go back and get another row. So the next row returns 1954, 1954. We plug that in, returns false. Next row, 1974, 1969. Finally, that returns true. Let's call it greater than equal to 5. What happens now? Store, or more precisely, since you're being asked to return the next tuple, you return it. So you iterate over the select iterator, iterates over all of the inputs until it finds one tuple that satisfies the condition, and then it returns it, and it saves its spot. So each iterator knows exactly where it is in its stream, and in order to, as long as the input to the select operator remembers where it is, the select operator doesn't need to do anything more interesting than that. So the select is going to return what? So Lamar Green, 1965 minus 1956, so true. Al, Michael Jordan, and every single time you call getNext, you're going to get another row from the select. All right, so we can then do the projection operator, and the projection operator is just going to get rid of a set of columns. It's going to read in a row, and just like the select operator, it's going to construct a new row to return, and the way projection works, it's just going to do that once for every row. Every time you call get next row, returns, it reads one row from its input, transforms it, and produces another row as output. So, random question. What would happen if we got rid of that where clause? What would we have to change? How would we... Yeah?
Remove the selection operator.
Okay, so we remove the selection operator. How would that change the code for the projection operator? Or the projection iterator?
It wouldn't have
Yep.
You'd have to read in from the source instead of from the selection iterator.
You would, yeah, so the only difference would be that you change the source that the projection iterator is reading from. The code for the projection operator, or the projection iterator, wouldn't change at all. The code for the player's iterator wouldn't change at all. The only difference is how you assemble the iterators together. All right, great. So one example down. Let's try something a little harder. Okay. And bring up visible. All right, so now we have something a little bit more interesting. There's a nested subquery in the from clause. So, guideline for translating nested subqueries. Whenever you need to translate a nested subquery, ignore the outer query. Look at the nested subquery first, completely in isolation. Hide the rest. So, can I do that? Hide everything other than the nested query. All right. So ignoring everything else, how would we translate just this portion of the query? Start with the from clause. So the from clause here has players. In fact, it has two copies of players. We're going to call them P1 and P2. So how do we combine them? What is
Cross product?
cross product? So the entire comma-separated list of relations that appear in the from clause get joined by a cross product. To be careful with my words here, get combined by a cross product. So we're going to have P1 and P2. If you have more than two, you can parenthesize them however you like. The reference implementation parenthesizes builds up the cross products left to right. So if you have P1 cross P2 cross P3, you can parenthesize this really either way. In the reference implementation, this gets turned into P1 cross P2 cross P3. P1 cross P2 cross P3. Clear? All right, now that you have the cross product, what's next? Selection. Okay, what am I selecting? P1 ID not equal to P2 ID. So I want all pairs of distinct players. All right, and next?
Question?
Yeah.
I'm usually used to not equal with exclamation points. Another way to put it.
Yeah, so greater than, less than, or sorry, less than, greater than is not is equal for not equals.
Okay.
Many will nowadays allow you to use bang equals, but a little nuance. Yeah, question? All right, so cross product selection, what's next? Bring up our handy dandy chart here. So we got the source, we got the where. The source, we got the where. No aggregates. No having, yeah.
Are there two different tables identically named players?
Yep. No, sorry, let me rephrase that. There is one table named players, but there's no limit on what you can put into a query. You can, as long as it's a relation. So if you want to have two copies of the same relation sitting in the same query, there's nothing to stop you from doing that. Does that address your?
Yeah, so with the from clause, we're just crossing the table with itself.
Yep. So we're finding all pairs of players that are different. Yeah.
What if the selection does not return anything since they're the same relation? So they all have the same IDs.
We don't have the same IDs. So let's do a really quick example here. Bring up my data sets. All right, and I'm going to keep this a little bit simpler so I don't have to copy the entire data set. But, so I got, let's say that I'm just working with the single ID column here. So we got FD, we've got MP. We've got GL, we've got AB or PA, and oops, it's backwards. Which is BF, PM, LG, A, B, MJ, A, R, and TS. So that's my players 1. All right, and I got players 2. D, DF, and pretty much the same thing. All right, what is P1 cross P2 going to look like?
A list of all possible pairs without.
All right, what's the first row going to look like?
DFDF.
DFDF. DFP, or depends on which one is on the inside of the nested loop, but either DFPM or PMDF. Let's say PMDF, LG, DF, and so forth. I'm not going to write everything else out. All right, let's apply our selection predicate to each of these. DFDF, is DF equal to DF or not equal to DF?
No.
No, so that one goes away. Is PM equal to DF or not equal to DF?
No.
Yes, so PM is not equal to DF. Good, that one stays. LG, DF. So does that address your concern? All right. All right, so we have one more step here. Which is the projection sitting on top of this. And I'm not going to write all that out, but Fn1, Fn2, and so forth. Yeah. The cross product of itself.
Yeah, or is this just kind of a standard idiom SQL?
So doing a cross-producting a table with itself is actually a standard idiom. It's referred to as a self-join. And it actually comes up in a lot of different cases. So if you've heard of graph databases, pretty much every single graph database query involves a really, really big set of self-joins. You really only have one relation in a graph database. Does that address your question? And I mean, there's cases where you want to do this, yeah?
Is it fine to draw your relational algebra going the opposite way as long as you know that that's the direction?
It's usually pretty clear because you start at the relations and you end at something else. So tradition dictates it this way, but you're not going to get penalized if you draw it upside down. Any other questions so far? Yeah.
Can we abbreviate like you have there? And stuff?
So for for handwriting, as long as the meaning is clear. If you're writing stuff, I'm super lazy. I can't expect you not to be just as lazy. So as long as the important thing is that you convey the idea of what you're trying to get across. If you can do that without writing it, without spelling everything else out, fine. All right, so the beautiful part of relational algebra, or one of the beautiful parts of relational algebra, is that everything is a relation. So this query here, I can take this entire query and I can hide the fact that that's a query. I mean, this defines a relation. And realistic, from the perspective of relational algebra, there's literally no difference between that and me just reading from a CSV file that contains what that would have produced. Literally no difference. So, if I want to read from this query, I could give it a name. I could call this entire relation subq. That is really good. There we go. Now, once I have that, I can look at the entire rest of the query, ignoring the fact that I have this nested subquery. I can basically just hide that entire nested subquery from my translation. I can hide this whole thing, ignore it, and just care about this relation subq. So ignoring that big nested subquery, how would I translate the rest of it? Start from the front clause, from the subtree. So start from the bottom. What's next? Oh. There we go. The where clause, all right. All right, next. Oh, sorry, there's an and in there. LS is greater than 2. Projection. All right, again, relational algebra, everything is a relation. So I can take this whole shebang, slot it in there, and it just makes a bigger tree. That's it. So basically, what I'll end up with, do this on the board, straightforward. What I'll end up with is the projection of first name, the selection of for season and then I have my subquery, which is another projection, another selection, and then the cross product of players with players. Questions so far? Yeah.
It's not really too related, but can you, if you have players P1 and players P2, can you use that in the outer? Can you like reference? So instead of having as, could you have done like select P1 by first name, or would that not?
Okay, so could you do select P1.first name? Yes, so if you don't have an as, the default for SQL is, there are basically two things that you do. If the expression that you have in there is just a variable reference, just a reference to one of the inputs, then it has the same name in the output. You basically, you can treat P1.first name, if there's no as, you can treat that as being equivalent to P1.first name as first name. In this particular case, that's not really a good idea because you have P1.first name and P2.first name, so both of those would generate an attribute with the same name, and that's a recipe for confusion.
Right, so if you left out the as on the outer layer, is there a way to differentiate between the two first names?
So the question is there a way to differentiate between the two first names? You wouldn't be able to refer to it as first name. I believe SQL has a way of positional column references. I could not off the top of my head tell you what that syntax is. Convention is do it this way.
Would people see these queries?
Yeah, I'm going to scan these in and put them on in place of slides. Yeah.
Could you reference P1?
Could you reference P1 in the outside? No. In general, the column names go away as soon as you get out of a select state, or the names in the from clause are only valid within the select statement that has the from clause. So from the perspective of the outside, this would be sub underscore q dot p1 dot first name, sub q dot p2 dot p2 underscore first name. Yep.
As an aggregate, right?
No, as is just a renaming.
Oh.
Any other questions? All right. So one more example, but I don't think we have enough time to pull it off entirely. So I will leave it with just the high points. We'll blast through this one really fast. So this one works pretty much exactly the same as the last one. You translate the nested query, again, just as before. The nested query in this case just has players. Oh, and there's actually a typo in this. And with a projection sitting on top of it, ID and so forth. Again, this whole thing gets renamed, and then you look at the outer query in its entirety.
projection, did you make a new column experience?
Yes. Okay. Now, the outer query has two markers that indicate that it is an aggregate query. The first one, there's an aggregate function, count, and the second one, there's a group by columns. Because of that, when we do the translation, the handy dandy chart once again, when we do the translation for the nested, for the outer query, rather that we're going to ignore the select, the projection operator, and instead we're going to use the aggregate operator. So once again, we have, in this case, we have no where clause, we have no cross product, we just have experience. And that feeds into a group by aggregate operator with experience and computing the count. Once again, count star just meaning count everything. Questions? Yeah.
Is it group by through projection then?
So both group by and projection change the schema of their inputs. So in that sense, group by and projection kind of seem a little bit similar, but group by and projection are actually very different. Group by operates on multiple rows or merges multiple rows into a single row, whereas projection, every row of input produces exactly one row of output. Does that make sense? I mean, spiritually they're quite similar, but just in terms of implementation, the code typically for a group by operator is going to look very different from the code for a projection operator. Let's really quickly go through an example on some data. All right, let's look at the nested query first, and let's even simplify that further and just say we're going to produce two columns, ID and experience. So what's that going to look like for our input data here? First row. First row of the projection operator. F. And experience DF and okay. May not be able to do math, but at least you have a memory. All right, Phil Martin. 0. Yep. And then so, let's actually finish this off. LG is 5. Is 5. AB is none. And MJ is 6. Yes, 18. 18. And let's do one more, 6, and then 10. Actually, it's not going to change here. All right, so we've got the inner component of query. Let's move to the outer one. So now we have to do a group by here. So we're going to scan over the elements here, visit the first row. We've got experience, and we've got the count. Now this all pretty much has to stay in memory to at least the way you do it initially. This all has to stay in memory until you're done computing over all of the inputs. So we're going to start the very first tuple. We're going to read one tuple from the group by operator is going to read one tuple from its input. It's going to find an appropriate group to put it in. In this case, the group by column is just experience. So we're going to find the group 2. So far, we don't actually have a group numbered 2. So we're going to create a group 2, and we're going to update the aggregate. In this case, the aggregate starts off at 0, and because we've just found one record, we're going to replace the count with 1. Next row, there's no group named 0. We create one. And once again, we update the count. We're going to iterate over this again. Let's say we have another basketball player. Let's call him OK. And no self-interest there. Clearly can't jump. And let's say that they've been active in basketball for all of 0 years, which is true. So now when I get to this next row, 0 already exists as a group. So rather than creating a new group, I don't need to create a new group. I just update the count to the next number. Any questions so far? Yeah.
So now the name of the column, since it's never given an alias, should it just be count star? Should it just be like?
You've discovered my secret ploy. So I answered this question for what happens when the column is just a column name. I did not answer it for all of the other cases. And the short answer is that the SQL spec does not actually define a name. It is up to you. I usually use something like expression 1, expression 2, expression 3, or aggregate 1, aggregate 2, aggregate 3, but that is entirely implementation dependent. So I think Postgres uses expr underscore something. Or sometimes you use just the function name. If there's a way to make it make sense, use that. If you can come up with a heuristic that kind of makes sense for presentation purposes, that's good practice, but the SQL spec doesn't say anything. Does that address your question? We're a little bit slow, so I'm just going to plow on. All right. All right. So first part of the discussion, how do you ask questions? How do you ask and answer questions? Second part of the discussion is now going to be how do you organize data so that you can answer questions efficiently. I have some data here. It's not particularly well organized. If I want to find, let's say, every row of this relation R where the column C is equal to 3, what would I have to do?
Go group by C,
Group by, what do you mean by?
as an order from 1 to 2 to 3, there's only 3 values, and everything from 3 will be located on the bottom of the list.
Okay, so I could, let's say I just had this data. I didn't have the ability to reorganize it or modify it. Just starting from this point. Your intuition is great. You actually, in general, you would want to organize the data. But let's say I just have that data as is. What do I have to do?
Just iterate through it all.
I have to scan through it all. I don't want to do that. So so I could potentially organize this data in a couple of different ways to make my life easier. Now, the first and simplest way to reorganize the data would be to sort it. So I take, if I want to specifically answer queries of the form, give me all rows where C is equal to some number, one thing I could do is sort all of the rows so that everything with C comes first. If I wanted to do something similar for A, I could, for example, sort all of my rows so that the A's were in order. So I get 6, 10, 3, 9, 8, 2, 12, 4, 3, 26, 2, 3, and so forth. Now, if I wanted to actually use that, what would I do? If I wanted to say, look up, give me an A where give me the row of R where A is equal to 12, or all of the rows where R is equal to 12. How could I efficiently implement that over this this now sorted list of records? Binary search. So I start at the middle. 12 is less than 28. I scoot up halfway through the everything coming before it, and I stumble across 12. Great. So having the data sorted is potentially useful. Now, what happens if I want to be able to answer queries both of the form, give me the, so I want to be able to answer two types of queries. One where A is equal to, can you see? Yeah. One where A is equal to some number. And I also want to be able to answer queries of the form C is equal to some number. So two independent types of queries. Select star from R where A is equal to some number, and select star from R where C is equal to some number. What are my options? Yeah.
You could have a copy of just the C attributes, and then we'll sort that, and then each one points to a pointer to the actual folder.
Okay, so one thing I could do is potentially keep an organized, organize my C's, and essentially have a little bit of a set of pointers, something that says, oh, by the way, there's a C with 1, and there's a C with 1. Or if I number all of these records, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then I could store, oh, by the way, record 6 as a 1 and record 7 as a 1. Same thing for 2 and 3. So I could say record 2 has a 2, record 8 has a 2, and that's it. And here I could say records 1, 3, 4, 5, 1, 3, 4, 5, 9, and 10. All have 3s. So this is the very simplest type of index. And it's referred to as a, these are the very simplest two types of indexes that you can have. And they're referred to as clustered indexes and unclustered indexes. And the reason for that is that here, this set of pointers is an organizational structure. It helps me locate my data, and I refer to it as an unclustered index because because the data itself isn't organized in a way that matches the organization of this index. So if I want to find all of the values of 2, I have to jump to this part of my data in order to get the full record, and then I have to move all the way to record 8 and read that part of my data. So in other words, in order to read from an unclustered index, we need to perform random accesses on the area where you're actually storing your data. And a clustered index is an index where all of the data is organized in some sort of way that corresponds to the lookup pattern that you're actually trying to do. I want to find all of the, let's say, A's between 12 and 35. I could do that as a range. I could do that by just iterating over successive elements of my data storage. Now, that doesn't really matter too much for data that's stored in memory. Where this actually starts becoming difficult is when your data gets stored on disk. So let's say that I have enough space in one page of data on disk to store 4 records, 4 full records. So this full chunk here will be 1 page. This full chunk here will be another page. And then I've got 2 stragglers that are going to go onto a different page. Now, if I want to do a read, if I want to find one specific record in this entire set of records, how many I/O operations am I going to need to do? How many pages am I going to need to load in off of disk? Yeah. 3. What do you say, 3? Okay, so I could load the entire record into the entire data set into memory, but let's say I'm looking for 12. Can I do better than loading in the entire, all of the pages? There's only one page that has it, and if I absolutely know that this particular page is the one that has the 12, I can jump right to it, load exactly one page. In general, do I know that? Do I have a way of just mysteriously guessing that that particular page contains a 12 on it? Yeah.
Not unless you index that column.
Not unless I build some sort of index. Not unless I save that information somewhere else. Now, I'm going to cheat and say that you can actually do a little bit better. You can do a binary search over the pages. But yeah, you want to, if you can have a little bit of extra information sitting outside of the data set, something that tells me, oh, by the way, or that summarizes, by the way, the contents of this page include anything from 6 to 26. The contents of this page include everything from 28 to 42, and the contents of this page are 43 to 45. That would be super helpful. And if I can keep that all in memory, because it's probably going to take up a lot less space, even better. Based on what I have in memory, if I know that 12 falls between 6 and 26, presumably I do, I can just jump to that one page and do one I/O operation. So where this kind of comes in is kind of represent this. You can write all this down in one big table. So if I want to do a lookup on a file where I know that all of the data is sorted by the attribute that I'm looking for, then I can, if I don't know anything else about that sorted file, I don't have any indexes over it, how long is that going to take? Log in, and specifically, log base. For a heap file, if everything's unsorted, what would it take? N. Okay. So I have to load the entire thing because I don't know exactly where my data is stored. All right. So help myself a little bit. So now we want some way of building an organizational structure over these data pages. So over here. And so I've got my data pages here. And I can keep in memory, let's say, some information about how this data is organized. So I've got my pages. Let's say this has records with keys from 1 to 4, 5 to 8, 9 to 12, 13 to 16, and so forth. I want to keep some sort of information that helps me pick out which page I need to go to in order to look up a particular record. So I presumably want to have some sort of pointer that points to each page, or some sort of reference that points to each page. And in order to help me figure out what goes where, I'm going to keep around a little bit of information, just one of the numbers that I can use to decide which page I need to look into. So the separator between those two pages is going to be 5. The separator between those two is 9, 13, and that's it. Okay, that's great. That works very nicely if I have only 4 pages. What if I need to store more pages? Have more data, and this is going to go off into infinity. I can build a tree structure in exactly the same way that I do a binary search. One tree structure with a set of pointers to these pages, and I can combine these further in higher-level tree structures. So now, maybe I can keep these in memory. Let's say that I can't. If each of these boxes represents one page that I need to load in off of disk, now how many lookups do I need to perform in order to read one record? Repeat the question? Okay. Yes, and I will repeat the question first. So let's say that each of these organizational structures, these lists of pointers, is enough to fill up one page. So in order to read this organizational structure, I need to perform one IO. In order to read this organizational structure, I need to perform one IO. So if I'm trying to find, let's say, 8, I need to read this one, then I need to read this one because 8 is less than, this would be 17. So 8 is less than 17, but larger than 1. I follow the left-hand side pointer. 8 is, what did I say, 7 is less than 9 but greater than 5. I follow this pointer. So I need to read, this page, and then this page. So in general, how many such reads am I going to need to do? Yeah?
The height of the tree?
The height of the tree. So if my tree has a branching factor of, let's say, k, so if I can store k pointers in one node, what is the height of the tree going to be? Log k. So we basically taken this log 2n and made it even smaller. Now we have log base k of n. Okay, so that's a little bit helpful. Now let's say I'm doing just equality predicates. Another way that I could store the information I need to store is to keep track of, to kind of put all of my data into buckets and make sure that I can keep track of where those buckets, what data went into which bucket. So let's say I have 2 buckets, or 2 buckets. So yeah, better get 4 buckets. So I've got bucket 1, got bucket 2, bucket 3, and bucket 4. Now I need some deterministic way of assigning records to buckets. And I can, in order to do that, I can use a hash function. In keeping with the hash function that I've been using, just to make things simple, I'm going to use a stupid hash function that you'd never actually use. Where the number, k mod the number of buckets, where in this case the number of buckets is 4. So I want to distribute my data across these buckets. Let's say that I want to organize my data based on the B column. So 10 mod 4 is 2. So we've got bucket 1, bucket 0, bucket 1, bucket 2, and then bucket 3. So 10 mod 2 falls in here. I put the record 6, 10, 3 into the first bucket. 3 mod 4 is, come on. The number is an easy one. So 35, 3, 1, again, so 2 hashes to 2, I put 43 to 3 into bucket 2. I keep going. I put all of the data all of the data into the corresponding buckets. Now let's say I wanted to do a lookup on, let's say I wanted to find records where B is equal to 7. What would I do? I'd look in bucket 3 or bin 3. So 7 mod 4 is 3. The hash value gives me back the number 3. So I'd look in so that means I look in bucket number 3. How many IOs was that? 1. I know exactly which bucket I need to look into. I perform exactly 1 IO. And so for a hash table, it's just 1. Wow, 1. That's amazing. Yeah.
Is that assuming that your bucket is just 1 page?
That is assuming that my bucket is just 1 page. In general, you want to pick your pick a number of buckets such that your hash function doesn't overflow. And while I'm not going to get into it this class, a couple of classes ago we talked about ways of resizing the number of hash buckets. So, wow, 1. That's amazing. Why don't I just use hash indexes for everything? 1 is certainly better than log kn, log 2n, log n, or just n. What do you? So I have to enumerate everything. What do you mean by that? You wouldn't be able to hash someone's name. So that's not entirely true. You can define a hash function in such a way that you can take any input: string, integer, date, text of Ulysses, whatever. Take a while, but yeah.
You can't use it for like range.
Range scans. Okay, so let's go back to our B tree here. How would I do? Let's say I wanted to find all records between 3 and 8. How would I do that?
You have to look up for 3, 4, 5, 6, and 8.
Okay, so I could look up every value individually. That's one way to do it. Could I do better? So that's going to be log n, log kn for every single lookup. Yeah?
Find where 3 starts, and then crawl the pages from 3 until you find something with 8.
What did I say? 3 to 8? Okay, so I start off my root. I find 3, which means all 3 is between 1 and 17, so I take my left branch. Need to load that in. 3 is less than 5, and I have nothing less than 5. So I read this page in, and that gives me 3, that gives me 4. Now I can go to the next page. Usually you'd store a B tree with a linked list between the pages. So you go to the next page, you have to load that in. That gives you 5, 6, 7, 8, and you're done. You've loaded in 2 pages. Wow, okay. So how, in general, how many operations is that going to take me? Yeah?
It's going to take 2 log,
2 log of k. Why do you say 2 log of k?
because you have to find the beginning and the end of the range.
Okay, so you have to find the beginning and the end. Do a quick example here. So let's say I wanted to find 3 to 19. So I'd find the beginning, that's here. I'd find the end, that's here. That was still substantially more records in there, more pages that I needed to load than, was it log? So that would be 3 plus 3. So you say I need to load 6 pages in, 6 pages in. Looks like I need to load in 1, 2, 3, double count that, 4, 5, 6, 7, 8, 9. So any suggestions on how to account for, there's some weirdness here. So in other words, I don't exactly agree with 2 log k, log base kn. Can we do better? Yeah?
Log k of n plus number of pages.
Okay, so I don't actually need to find the endpoints manually because as I keep scanning records, I'm eventually going to hit the end. And I know exactly when I've hit the end. So, here we go. So in order to do a scan over a B tree index, I need to do log k and define the start. But then I'd also just need to put in the number of pages that I actually need to return. What about for a hash index? Could I do anything similar? Bring my hash index up here. So let's say I wanted to find everything between 3 and 8. So I could, in principle, enumerate every single value that fell between 3 and 8, load the corresponding pages, and I'd have my records. Okay, that actually assumes that the numbers are enumerable. So if I have integers, integers are kind of weird. If I have integers between 1 and 10, yeah, maybe it's feasible. If I have integers between 1 and a million or 1 in a billion, I don't really want to do a billion operations, a billion IOs, just to find everything. So in general, for a hash, if you wanted to do a scan, this degrades essentially to n. And since we're basically running out of time here, I'm going to fill in the rest of these. Sorted file relates to B tree in pretty much the same way for scans, and scans for heap files are also n. So the trade-off here, in general, if you have the ability to create an index, either a B plus tree or a hash are a good way of organizing your data. The B plus tree gives you faster scans, and the hash index gives you faster lookups. I don't have enough time to go over the join algorithms, but that was the last thing I was going to cover. So, any final questions? All right. Anyone who hasn't turned in their homework, down here, and good luck on Tuesday.
Yes, I would. And also, yeah, Monday, we should definitely.
So basically, the key is time for leaders and separate our values.
Yeah, I want to get that done. Early next Yes. Yeah, we have. All right. Sounds
It would so, as a convention, it would. Three is the interesting so in practice, it actually kind of as a convention because that if you join on the B, then because it's equally joined, it doesn't matter what the so that's more of a simplification for the sanity of someone writing in fact, before you have implementation, cross-product, if you have cross-product installation, you can join cross-product installation first, then yeah.